Okay, we're up to section 6.3, the Bohr theory, or Bohr's theory, Niels Bohr, his theory of the hydrogen atom. The Bohr theory was designed originally to explain a phenomenon called line spectra. And so Bohr turned his attention to the simplest element in the periodic table, which was the hydrogen atom, H. The hydrogen atom, from a structural perspective, is very, very simple. It has a nucleus with one proton and an electron. The proton is positively charged. The electron has an equal amount of charge, but it's the opposite, it's negative. So the two particles are attracted to each other via electrostatic attraction. Now, some hydrogen atoms, a small percentage of them have a neutron in the nucleus as well, but the vast majority of hydrogen atoms are just the proton and the electron. So if you're trying to determine the structure of the atom, the hydrogen atom is a pretty good place to start because it's not very complicated, or at least it doesn't seem as though it's very complicated. So here's what was observed in his time. We can do this experiment pretty easily these days. What we do is we take a glass tube. It's called a discharge tube. It's represented here in the diagram on the left. And we apply a high voltage to it. So we put a gas inside the tube, and in this case it'll be hydrogen. And the hydrogen will emit, it will release photons of light, and it'll glow. And it appears almost kind of reddish when hydrogen glows. And some of that light can be blocked, or much of it can be blocked, and a small amount of it can be allowed through a slit, through a small opening. That ensures that the light is moving in one direction. And that light is then sent through a prism. And what a prism does is it uses an index of refraction. It bends light, and it turns out light bends at an angle that depends on its wavelength. And so when you do this, when you put light from the hydrogen through the prism, you get four visible colors. And those four visible colors are shown in the diagram right there in the center. The light is separated into various components. These are different wavelengths. One of them is red, one of them is blue, one of them is purple, and the other one's, well, actually, let's do indigo, and the other one is violet. So if we show those four lines, they're called lines because they're at very specific wavelengths, and together we call that a spectrum. What we see is that there is an emission at a wavelength of around 410 nanometers. And then there's another one at 434 nanometers, another one at 486 nanometers, and then finally one at 656 nanometers. That's shown on the diagram down at the bottom. So the issue here is, why does hydrogen, when it emits light, only emit these four specific colors, or these four specific wavelengths of light? Why doesn't it emit all different colors like a light bulb does, right? A light bulb produces white light. There's all kinds of different wavelengths that are produced. So that was what Bohr wanted to work on. Now let's go a little bit further into the data. It turns out that there is more than just those four colors. There are also colors in the ultraviolet region, so we can't see those, and in fact, we would need specialized equipment to be able to run the experiment to where we could observe the ultraviolet rays. And there's two in the infrared, two different ranges of colors in the infrared, which again, we can't see those with our eyes. So these four groupings of light, or electromagnetic waves, are called the Lyman series, Lyman, and that occurs in the ultraviolet range. There's the Balmer series, which is in the visible, the Paschen, which is in the infrared, and the bracket, which is also in the infrared. So in fact, the hydrogen atom is emitting many different lights, many different colors, I should say, some of which are visible and others are not. And it turns out that other elements do the same thing. If you were to heat up lithium atoms and allow them to glow, they would produce light as well. And that light would have a line spectrum and it would have specific colors. Each element has its own specific set of colors that it emits when it's heated up as a gas. In fact, this is how astronomers can determine which elements are present in stars. Because if you think about it, stars are producing light all the time. They have elements in them, primarily hydrogen and helium, but other elements as well. And so the stars produce lots of different colors, and you can match up like a fingerprint the spectrum of colors that are being emitted by a particular star and determine which elements are in that star. So when stars are very young, they tend to possess a lot of hydrogen, but as they get older, they possess more and more heavier elements, and you can see that aging take place in different stars. Okay? So the fingerprinting is a nice analytical tool we can use to determine the presence of specific elements in a sample. In fact, you heat the sample up, we'll come back over here to the first figure, you heat the sample up, measure what colors are emitted, and match that up with a little library catalog of which element that you have. And it works very, very nicely. So now what we want to do is we want to talk a little bit about what's going on. Like, why is it that hydrogen is doing this? And that's what Bohr set his mind to, was to figure that out. And it turns out there had already been some information or some analysis of this done in previous generations. Johannes Rydberg, he actually figured out that he could match up these specific wavelengths just mathematically. So he wasn't looking at the physics of what was happening, but he was just trying to match up the pattern of these wavelengths. And he came up with an equation which relates the wavelength of light to what we now call quantum numbers. So R, which we would call the Rydberg constant, and this whole thing here is called the Rydberg equation. And this R value is the Rydberg constant. And the Rydberg constant has a value. Take out a look. I'm going to actually go ahead and write out all the sig figs here. 1.0973 7316 times 10 to the minus 7 reciprocal meters, MKS system. So what this says is 1 divided by the wavelength is equal to this constant, the Rydberg constant, R, times 1 over n1 squared minus 1 over n2 squared, where n1 is a number of 2, 3, 4, 5, 6, etc. And n2 is the same. It's 1, 2, 3, 4, 5, so forth and so on. The point being that the value of n2 has got to be less than the value of n1. Okay? So if n1 is 2, n2 would have to be 1. If n1 is 5, n2 would have to be 1, 2, 3, or 4. It has to be less than n1. And it turns out he was able to match these up, and the results of this are shown here in table 6.1. The Lyman series is the case where n1 is equal to 2 or 3 or 4, and n2 or n final is equal to 1. You'll see different subscripts used for these types of analyses. The Bohrs series, that's the one invisible, that's where n3 might be 3, but n1 might be 3 or 4 or 5, but n2 would be 2. The Paschen series, n1 would be 4, 5, or 6, but n2 or n final would be 3, and so forth and so on. Okay, so we can match up all of those different colors, only a few of which we can actually see with our eyes, but technology can be used to detect any of them. We can match those up with the Bohrs equation. I'm sorry, the Rydberg equation. Now, that doesn't give us a physical interpretation of what's happening. All it does for us is gives us a mathematical relation. So it was up to Bohr. Bohr was the one who came forward and figured out that we could apply physics to this problem. Because we know the problem. Essentially, it's the problem of a positively charged particle attracted to a negatively charged particle, mutual attraction via electrostatics, right? We're going to ignore gravity. Gravity is so weak when we're talking about the masses of these particles, it's negligible. So it's really just electrostatic attraction. These two particles are attracted to each other. So he said, well, wait a minute. If the electron weighs a lot less than the proton, which it does, the mass of the electron is less than 1,000th that of the proton, then what we might expect is that the electron is essentially in orbit, perhaps a circular orbit around the proton. Okay? Now, in fact, you can get more complicated about this and say that, hey, they're actually both in orbit around each other. They're both moving, but it's effectively the electron, because it's so much lighter than the proton, it does almost all the motion. And then he said, okay, so here's our physical picture. Can we figure out what the energy of attraction would be between those two particles? And that problem had been worked out years before. The energy of attraction has to do with a constant times the charge of the proton times the charge of the electron. So I'll write that as Q plus times Q minus, divided by the distance between them. So I'm going to write that as R. And I'm going to put a negative sign in front of it to indicate that this attractive force is negative. Negative energy. Negative energy means that it's attractive. So this is an attractive energy. Okay, the proton and the electron are attracted to each other. And let's write down the charges. The charge of the proton is 1.602 times 10 to the minus 19 coulombs. And to all experimental results, the charge of the electron is equal and opposite. They are equal to each other, just opposite signs. Okay? Can't see any difference in those numbers. And we're not going to worry about the constant here. We're not going to use this. If you take a physics course, you'll do calculations where you have to know the value of K and you use it in your calculations. But we're not going to worry about here. Okay? So that's the energy of attraction. If this were just a normal situation where you had a positive charge with a negative charge in orbit around it. But what Bohr noticed was that light is getting emitted. So he suggested maybe what's happening is the electron is changing its distance from the proton. See how you have this R down here? If you change the distance R, you change the energy of attraction. So what he suggested was perhaps what's happening is every time that light is released by the atom, by the hydrogen atom, it's a result of the energy of attraction changing because the electron is changing the distance that it's at from the proton. So meaning that if the electron were over here, it would have a different energy of attraction. And so what he did was he said, hey, wait a minute. We're getting these line spectra, so we're getting very specific wavelengths, right? Lambda 1, lambda 2, lambda 3, at very specific colors. Maybe each of these emissions corresponds to a transition where the electron, which is negatively charged, is moving from one orbit to another. It's jumping from one, we now call this quantum level. So from one quantum level to another. And the fact is, he suggested, the electron can only exist in very specific quantum levels, and when the electron moves from one level to another, it emits a photon of light with one of these very specific wavelengths. And that's his idea. That's essentially his idea. So let me put it into another picture. And make it a little bit closer to what Bohr was saying. So you have the proton at the center, and then the electron is going to occupy a specific orbit at one time. It can't exist in more than one orbit at a time, and it cannot exist, I'm sorry that these circles aren't so great, it cannot exist in between these orbits. So I'm just going to draw a few of them. Concentric circles. And then you could label them n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. So the electron might be in n equals 6. I'm going to draw a little ball there for the electron. It might jump down to n equals 2. That's called a transition. And we can represent it as n equals 6 goes to n equals 2. What that means is the initial value, n initial, or n1, and then n final, or n2, would be the final state. So the electron goes from 6 to 2. And he argued that any time the electron moves from a higher level to a lower level, a higher quantum number to a lower quantum number, the energy of the atom changes because the distance changes. And that energy difference, delta E, so I'm going to write it this way. E6 minus E2, right? So that's the energy of each level, is equal to delta E. And he said that that delta E is equal to the energy of a photon that is emitted when this occurs. So the electron jumps down, and when that happens, the atom emits a photon, one particle, one quantum energy. And the energy of that photon is equal to the energy difference between those two levels. It's absolutely brilliant idea, right? So if the electron goes, let's say, from n equals 4 down to n equals 1, right? So n equals 4 goes to n equals 1. The difference in energy between those two levels, E4 minus E1. Well, actually, to be honest with you, we should do final minus initial. So it really should be E1 minus E4, but we won't worry about that for right now. That difference in energy would be the energy of the photon that is emitted in that process. Absolutely brilliant idea. So this will right? So energy is conserved, right? We're not creating or destroying energy. What we're saying is the electron spontaneously, it jumps back down to this lower level and emits a photon in the process. And the energy of that photon is equal to the difference in energy between those two levels, between those two quantum levels. And if you want to have an analogy would be a staircase. The potential energy, the gravitational potential energy of your foot is quantized, right? Because there's only certain levels. Now, in fact, it's not really quantized because you could move your foot up higher this way. It's just only on the levels. It's on the steps that it's quantized. You actually have to move your foot like that. But Bohrs said no. The electron can be in this state, it can be in this state, it can be in this state, so forth and so on, but it cannot be in between those states. Okay? And he could go on and he could say, wait a minute, hey, you know, let's apply physics to this, but what I'm going to do is I'm going to modernize this calculation for the atom. I'm going to adapt it. And I'm going to say the energy of the electron at any level, any value of n, 1, 2, 3, 4, 5, and 6. By the way, there's no zero. There is no zero in this calculation. It's 1, 2, 3, 4, 5. Discrete values, we call those. It's going to be equal to minus 2.18. Again, it's attractive. 10 to the negative 18 joules times 1 over the level it's in squared. And if you look at that equation, that energy level, that calculation, so n can be 1 or 2 or 3 or 4, so forth and so on, that looks a little bit like Rydberg's equation. Right? You got this n squared in there, and then you got a constant in there, and that's related to the wavelength. Well, we know that energy is related to wavelength from the previous section. We now have a connection. Bohr's connection is what we're talking about right here. So it's a very interesting physical model. Now I want to show you just a couple little details of some tidbits of information here. And one is, what happens if you remove the electron from the atom? Let me erase that and spell that correctly. That process is called ionization. So essentially what you're doing is you're taking a hydrogen atom, which has one electron. I'll represent the electron as a dot. You're removing it from the atom, so you get H+. And then you also have a separate electron over here. That's called ionization. How much energy would it take to do that, right? Well, what we would do is we can calculate that, but first I want to figure out what is the energy associated with having the electron removed. And essentially what you're doing is you're letting the electron go so far away from the nucleus that it's approaching infinity, right? It approaches a very, very large number. So mathematically, you would have 1 over something that is approaching infinity. Okay? And what happens is if you take 1 over a very large number, a very, very large number, 1 over a very large number approaches 0. So it approaches 0. So in other words, if the electron is removed completely from the atom, there is no attractive energy anymore, right? And that makes sense, right? If the electron's not even on the atom, they're not attracted to each other anymore. So it would be 0. And so we can show that mathematically using Bohr's equation there. Now, we can take his equation and go even further, and that's what he did. He did all sorts of manipulations here.